DNA tests promise to reveal who we are, but the truth is far more complicated. Behind the glowing charts and tidy percentages, entire genetic origins vanish in silence. Some lineages are too ancient, too rare, or deliberately hidden by history. Maps of ancestry light up one region, while whole civilizations remain erased in shadow. Your results may say 90% complete, yet the most mysterious part of your DNA is missing. This is the story of why ancestry tests fail, and the forgotten genetic origins they can never show. The Basques of northern Iberia represent one of Europe's most enduring genetic mysteries. Their language, Euskera, stands as a complete isolate with no demonstrable relationship to any other known language family, surviving as a relic from prehistoric Europe when the continent spoke dozens of now extinct tongues. This linguistic anomaly sparked decades of speculation about Basque origins, with theories ranging from direct Paleolithic continuity to connections with ancient Caucasian populations. Recent genome-wide analyses have revealed the Basques derive primarily from the same ancestral components as their neighbours, early European farmers and Western hunter-gatherers, supplemented by approximately 25 to 30% steppe-related ancestry that arrived during the Bronze Age. However, the truly mysterious aspect of Basque genetics lies not in their ancient origins, but in their subsequent evolutionary trajectory. Since the Iron Age, roughly 2,800 years ago, the Basque population has maintained remarkable genetic isolation, despite occupying strategically important territories that witnessed extensive Roman colonization, Visigothic rule, and medieval Christian kingdoms. This isolation becomes even more puzzling when considering that Basque territories were never geographically inaccessible. The region encompassed important mountain passes and coastal areas that served as crucial trade routes between Iberia and the rest of Europe. Archaeological evidence demonstrates continuous cultural exchange with neighbouring populations, yet genetic data shows minimal gene flow during periods when other Iberian populations were being substantially altered by successive waves of migration and conquest. The Basque genetic signature is further distinguished by specific lineage enrichments that suggest either founder effects or selective pressures unique to the region. Y chromosome haplogroup R 1b DF27 reaches frequencies among Basques that exceed those found in neighbouring populations, while mitochondrial DNA shows elevated levels of haplogroups H1, H3 and U5 lineages that trace back to different phases of European prehistory. Some researchers propose that Basque genetic isolation resulted from cultural practices that limited intermarriage with outsiders, while others suggest that the mountainous terrain provided sufficient refuge during periods of population replacement that affected surrounding regions. The Basque population exhibits the world's highest frequency of Rh-negative blood type, with rates reaching 25 to 35% compared to global averages of 10 to 15%. This distinctive hematological signature has fueled speculation about ancient origins and possible connections to pre-modern human populations. Some researchers have investigated whether Basques retain elevated levels of Neanderthal ancestry, given their geographic location in southwestern Europe where Neanderthals persisted longest. However, genomic analysis reveals that Basques actually carry similar or slightly lower levels of Neanderthal DNA compared to other Europeans, typically around 1 to 2%. The high Rh-negative frequency likely reflects genetic drift and founder effects within their isolated population, rather than archaic human admixture. Sardinia harbours what researchers describe as a genetic time capsule, a population that preserves the most complete snapshot of early European farmer ancestry found anywhere in the modern world. Contemporary Sardinians carry an extraordinary 80 to 90% early European farmer component in their genomes, representing genetic continuity spanning over 8,000 years. This preservation is remarkable not merely for its extent, but for its persistence despite Sardinia's position at the crossroads of ancient Mediterranean civilizations. The island's strategic location made it a coveted territory for successive maritime powers. Phoenicians established trading posts and mining operations, extracting Sardinian silver and lead for their expanding commercial networks. Romans conquered the island in 238 BC, incorporating it as one of their earliest provinces and introducing Latin culture, urban planning, and agricultural innovations. Vandals, Byzantines, Pisans followed, each leaving archaeological traces of their presence. Yet genetic analysis reveals that these historical conquests and cultural exchanges left surprisingly minimal impact on the Sardinian gene pool. The mystery deepens when considering that island populations typically experience genetic drift and founder effects that can dramatically alter their genetic composition over time. Sardinia's large size and substantial population should have made it more susceptible to genetic change from incoming populations, not less. However, demographic modelling suggests that the island maintained effective population sizes large enough to resist random genetic drift, while somehow limiting gene flow from immigrant populations. Sardinian genetic distinctiveness manifests in several ways beyond overall ancestry proportions. The island shows elevated frequencies of Y chromosome haplogroups, both of which have ancient European origins but follow different distribution patterns on the mainland. Mitochondrial DNA analysis reveals high frequencies of haplogroups H3, J2, and U5, creating a combination that distinguishes Sardinians from other Mediterranean populations. These lineages suggest that early European farmers who colonized Sardinia carried a somewhat different genetic makeup than those who settled the mainland, possibly reflecting different source populations or different phases of the Neolithic expansion. The indigenous Sami people of northern Scandinavia embody a genetic paradox that bridges two continents. Their genomes contain a substantial component, comprising 25 to 40% of their total ancestry. That shows clear affinity to Siberian populations, particularly the Nganasan people of the remote Taimyr Peninsula. This Siberian-related ancestry entered Fennoscandia at least 3,500 years ago, creating a unique population that combines European and Asian genetic elements in proportions found nowhere else in the world. The mystery begins with the migration route itself. How did a population carrying Nganasan-like ancestry traverse the vast distances between central Siberia and Scandinavia? The most parsimonious explanation involves a northern route across the Eurasian Arctic, but archaeological evidence for such a migration remains sparse. Alternative theories propose southern routes through the Eurasian steppe, but these would require explaining how Siberian-related populations reached Scandinavia without leaving detectable genetic traces in intervening European populations. The timing of this migration coincides with significant climatic and cultural changes in northern Europe. The Late Bronze Age period, around 3,500 years ago, saw the emergence of distinctive Arctic-adapted cultures in Fennoscandia, including the development of reindeer herding practices that became central to Sami identity. Whether the arrival of Siberian-related populations brought these cultural innovations, or whether cultural changes facilitated the integration of incoming populations, remains unclear. Modern Sami genetic structure reveals additional complexities that compound the mystery. Different Sami groups show varying proportions of Siberian-related ancestry, with some populations carrying up to 40%, while others show levels closer to 25%. This variation doesn't correlate clearly with geographical distance from Siberia, suggesting that the admixture process involved multiple events, or that subsequent population dynamics redistributed ancestral components in unexpected ways. The Sami Y chromosome profile shows strong enrichment for haplogroup N1C, which follows a distribution pattern that connects northern Europe to Siberia and East Asia. However, the specific N1C sublineages found among the Sami differ from those in other Finno-Ugric populations. Mitochondrial DNA analysis reveals elevated frequencies of haplogroup U5B1B1, a lineage that appears to have European rather than Asian origins, creating a pattern where maternal and paternal lineages tell different stories about Sami population history. The Etruscans of ancient Italy have fascinated scholars since antiquity, when Herodotus claimed they migrated from Lydia in Anatolia, while Dionysius of Halicarnassus argued for local Italian origins. Their non-Indo-European language, distinctive art, and sophisticated urban civilization seem to set them apart from other Italian peoples, fueling centuries of speculation about their mysterious origins. Modern genetic analysis has not only resolved this ancient debate, but revealed unexpected complexities in Etruscan population history that illuminate broader patterns of demographic change in ancient Italy. Genome-wide data from Etruscan individuals dating to 800 to 500 BC definitively disprove theories of recent Anatolian origin. Instead, Etruscan genomes show substantial steppe-derived ancestry, comprising 30 to 40% of their total genomic composition, levels virtually identical to contemporary Latin populations. This genetic similarity suggests that Etruscans and other Iron Age Italian peoples shared common demographic origins rooted in the Bronze Age population movements that brought steppe-related ancestry to the Italian peninsula. However, the Etruscan genetic story takes unexpected turns during the Roman imperial period. Samples dating to the height of Roman power show dramatic increases in Eastern Mediterranean ancestry, with genetic profiles shifting toward those characteristic of populations from Greece, Anatolia, and the Levant. This transformation likely reflects the cosmopolitan nature of Roman society, where slavery, trade, and military service brought populations from across the Mediterranean world into Italian territories. The most surprising discovery involves the partial genetic reversal documented in early medieval samples. Following the collapse of Roman imperial authority, Etruscan region populations show genetic profiles that shift back toward earlier, more Italian configurations. This pattern suggests that the demographic changes of the imperial period were not permanent replacements, but rather temporary alterations that were later reversed through processes that remain poorly understood. The Irish travellers represent a fascinating example of recent population divergence that has produced genetic patterns typically associated with much more ancient separations. Despite comprising a distinct endogamous community within Ireland, travellers diverged from the settled Irish population only approximately 12 generations ago, roughly 360 years based on genetic estimates. This recent separation makes their genetic distinctiveness all the more remarkable and provides insights into how quickly isolated populations can develop unique genetic signatures. Traveller genomes show the same basic ancestral components as other Irish populations, reflecting the steppe-rich Bronze Age ancestry that characterises Atlantic European populations. However, centuries of endogamy have produced elevated levels of genetic drift and runs of homozygosity that distinguish travellers from their settled Irish neighbours. These patterns mirror those typically observed in much more anciently separated populations, demonstrating how cultural practices can accelerate genetic differentiation even within short time frames. The timing of traveller population formation coincides with significant social and economic upheavals in Irish history, including the effects of English colonisation, land confiscation, and economic displacement that created mobile populations throughout Ireland. However, genetic evidence suggests that travellers did not originate from a single founding event, but rather from the gradual coalescence of individuals and families who adopted itinerant lifestyles during this period of social disruption. Modern traveller populations show internal genetic structure that reflects their historical organisation into distinct family groups, with strong preferences for endogamous marriage. Different traveller families carry different combinations of ancestral lineages, suggesting that the founding population drew from genetically diverse segments of the Irish population. However, subsequent genetic drift within family groups has created detectable genetic differences between traveller clans, patterns that provide insights into how cultural organisation can shape genetic structure within isolated communities. The genetic history of Europe's Romani populations represents one of the most remarkable migration stories preserved in the human genome. Multiple independent analyses using different methodological approaches have converged on a consistent narrative. Romani populations originated in northwestern India approximately 1500 years ago and entered Europe through the Balkans around 900 years ago. However, this consensus masks considerable complexity in the details of Romani population history and the processes that shape their distinctive genetic profile. Modern Romani populations across Europe carry 50 to 60% South Asian ancestry, with the remainder derived from various European populations encountered during their westward migration. This admixture pattern creates a genetic signature that is immediately recognizable and distinguishes Romani individuals from all other European populations. However, the specific South Asian source populations remain somewhat mysterious, as modern northwestern Indian populations have themselves been altered by subsequent migrations and demographic changes. Y chromosome analysis reveals that Romani populations carry South Asian haplogroups H1A1AM82 and R1AZ93, alongside European lineages I1 and J2, creating combinations that reflect both their origins and their migration history. The European Y chromosome lineages show geographical patterns that suggest multiple admixture events during the Romani migration across Europe, with different Romani groups carrying different combinations of European paternal lineages, depending on their specific migration routes and settlement histories. The mystery deepens when considering the social and cultural mechanisms that enabled Romani populations to maintain their genetic distinctiveness while dispersing across an entire continent. Most migrating populations either assimilate into local communities or establish localized settlements that become integrated into regional population structures. The Ainu people of Hokkaido represent the closest living connection to Japan's prehistoric Jomon culture, carrying an extraordinary 80% Jomon ancestry in their genomes. This genetic preservation is remarkable, given that mainland Japanese populations derive from complex layering of Jomon, Yayoi, and later continental ancestries that have substantially diluted Jomon genetic signatures elsewhere in the archipelago. The Ainu genetic profile raises profound questions about the processes that enabled such complete preservation of ancient ancestry in the face of successive waves of migration and cultural change. The Jomon period in Japanese prehistory lasted from approximately 16,000 to 3,000 years ago and was characterized by hunter-gatherer societies that developed sophisticated pottery traditions, complex settlement patterns, and distinctive physical anthropological features. Ainu Y chromosome profiles show strong enrichment for haplogroups D1b and C1a1, both of which have deep roots in East Asian population history, but follow distribution patterns that distinguish them from lineages common in modern East Asian populations. Haplogroup D1b is particularly intriguing because it represents an ancient lineage that is now found primarily in Japan and Tibet, suggesting ancient population connections that predate the major demographic changes of the last few millennia. Mitochondrial DNA analysis reveals elevated frequencies of haplogroups N9 and G1b, lineages that show clear associations with Jomon populations, and distinguish Ainu from both modern Japanese and other East Asian populations. The specific sublineages found among the Ainu often represent deeply divergent branches within these haplogroup families, suggesting long periods of genetic isolation that allowed rare ancestral variants to persist. The mechanisms that enabled Ainu genetic preservation remain poorly understood. Geographic isolation in northern Hokkaido may have provided some protection from population replacement, but the island was not completely isolated from cultural and demographic changes affecting the rest of Japan. Archaeological evidence shows that Ainu populations maintained trade relationships with both Japanese and continental Asian populations, suggesting that cultural exchange did not necessarily result in substantial gene flow. The island of Madagascar harbours one of humanity's most extraordinary population fusions, where Austronesian seafarers from Southeast Asia encountered Bantu-speaking peoples from East Africa to create the modern Malagasy population. Genetic analysis reveals an almost perfectly balanced admixture comprising approximately 50% Austronesian ancestry, most similar to populations from Borneo, and 50% Bantu African ancestry, with the fusion occurring roughly 1,000 years ago during Madagascar's initial human colonization. The discovery of this balanced admixture immediately raised questions about the demographic and social processes that could produce such even proportions of ancestry from two continents. Most population admixture events result in highly uneven ancestry proportions that reflect the relative sizes and social positions of the mixing populations. The Malagasy case suggests either that the founding Austronesian and African populations were roughly equal in size, or that specific social and cultural factors promoted balanced reproduction between the two groups. Further analysis reveals a pattern that provides crucial insights into the colonization process. Maternal lineages, traced through mitochondrial DNA, show predominantly African origins, with haplogroups L2 and related lineages comprising the majority of Malagasy maternal ancestry. Conversely, paternal lineages traced through Y chromosome analysis show predominantly Austronesian origins, with haplogroup O1A2 and related lineages accounting for most Malagasy paternal ancestry. This gender-biased pattern suggests that the initial colonization involved predominantly male Austronesian seafarers, who established relationships with African women, possibly including enslaved individuals, transported from the mainland or African populations, who had already established settlements on the island. However, the balanced overall ancestry proportions indicate that this initial pattern was subsequently modified by additional migration events, or demographic processes, that brought the total ancestry proportions into near-perfect balance. The timing and logistics of Madagascar's colonization remain subjects of active research and debate. Archaeological evidence suggests human presence on the island by at least 2,000 years ago, but the genetic data indicating major population fusion around 1,000 years ago implies either that earlier settlements left minimal genetic legacy, or that the major demographic changes occurred during a secondary colonization phase. The coordination required for Austronesian populations to traverse the Indian Ocean and encounter African populations on Madagascar suggests sophisticated maritime capabilities and possibly planned colonization efforts rather than accidental settlement. The term Black Irish has captivated popular imagination for generations, used primarily to describe people of Irish descent with dark hair, dark eyes, and sometimes more Mediterranean-appearing features. This designation has become entangled with romantic myths that persist despite overwhelming genetic and historical evidence to the contrary, representing one of the most enduring misconceptions in popular genealogy. Modern Irish genetic composition reflects a complex layering of ancient migrations, rather than recent exotic admixture. Irish people derive most of their ancestry from Western steppe herders, who arrived in Western Europe during the Bronze Age, carrying genetic signatures that connect them most closely to other Atlantic European populations. DNA studies reveal that Irish males predominantly carry the R1b haplogroup, particularly R1b M269, which is common across Western Europe, while Irish females belong to diverse mitochondrial DNA haplogroups, reflecting ancient European lineages. Crucially, genetic analysis has established that the closest genetic relatives of the Irish in Europe are found in northern Spain's Basque country. This genetic affinity reflects ancient population connections predating recorded history by millennia rather than recent admixture events. Analysis of ancient Irish remains shows that early farming populations were closely related to southern European groups, especially those from Spain and Sardinia. The most persistent myth surrounding Black Irish origins involves the Spanish Armada of 1588, suggesting that dark-featured Irish people descended from Spanish sailors who survived shipwrecks off the Irish coast and subsequently intermarried with local women. However, no anthropological, historical, or genetic research supports this romantic narrative.